Okay. All right. Great. So let's go ahead and keep going. We're almost done with chapter 10. We have just a little bit left, and then we'll start on chapter 6, which is moving us in a different direction. I just wanted to make a comment that the third laboratory report, which I think is the vinegar titration, I will start working on grading those this week. So they should be done by the end of the weekend. Okay. And then I'll update the scores on Alex for that. So that should come up in the next week or so. Okay. Good. So let's talk about gases. We were looking at the kinetic molecular theory of gases, but we hadn't completed it. So let's take a look here. I'm going to come back to this. It's been the whole weekend. So let's take a look at it. Okay, so the idea here is that we have really a few properties of gases that we want to look at. And it's based on what we call a model or a theory. And the model or the theory is that you've got these little particles. They're tiny and they're widely spaced on average. They're very far away from each other. And here's what we can say about pressure. We've talked about pressure a lot, right? We did all of those calculations of converting pressures, using it in the ideal gas law, all of those calculations, right? To say that the pressure is larger or greater, really what that means is there's a greater density. If you put more gas particles in the same space, you're increasing the pressure. Okay? So pressure, in a sense, is a measure of the density of a gas, because the more that you put in there, the larger the pressure is going to be. Okay. Now, let's put these gas molecules in a container. And then let's consider the fact that they're not stationary. Solids are stationary, but gases are not stationary. They're moving. These particles are moving in different directions, right? They're moving in all random motion. Some of them are moving slow. Some of them are moving fast. But they're all moving, okay? Now, things change, right? So if I open up the little door over here, if I put a door here or a window and I open them up, then they're all going to stream out, right? But if it's all closed off, they're just sort of moving around in different, each with its own specific velocity. So typically when you see notation like this, where they use arrows, the longer the arrow, the faster they're moving. It's a vector, essentially. So these vectors, these arrows, are showing you the direction they're moving, but also how fast they're moving relatively by showing the length of the arrows. So if an arrow is really short, that means it's moving not as fast as the other ones. Okay. So what we said was there's a couple of aspects of a gas that we should consider. One is kinetic energy. The kinetic energy of a gas depends on the temperature. In fact, there's even a calculation for that. The average kinetic energy. So I'm going to put E sub K, and then I'm going to put a little line above it. The little line means average, okay? When you see that line above it, that means average. So the average kinetic energy is 3/2 RT. Interesting. Very simple equation. And the R is the gas constant, 8.314 joules per mole K. So typically, we don't use the 0.082057 for this equation. Anytime we're dealing with energy units, we want to use the 8.314, or you could do it in kilojoules, times 10 to the minus 3 kilojoules per mole Kelvin. So sometimes you'll see it that way too. Either one is fine, as long as it's got joules in there somewhere, okay? So what that tells us is that the average, remember, these are all moving at their own speeds. So some are moving faster, some are moving slower. So there's an average speed that they're moving, right? The average kinetic energy that these gas molecules have is very simple. It's 3/2 times R, where R is this constant here, times the T. Remember, when we're dealing with gases, this has got to be in Kelvin, right? So we're not going to have like negative 50 degrees Celsius or 0 degrees Celsius. All the values of temperature have to be positive. That's why we use the Kelvin scale. Okay. Otherwise, you would have negative energies or 0 energies. And so we have to use the Kelvin scale. Okay. So it's relatively simple, 3/2 RT. And that gives you the average kinetic energy. But we can also say that if you talk about the kinetic energy of one particle, right? If you just have one particle moving, we said earlier in the course that that's 1/2 m. Did I use u or did I use v? I'm going to use a v for velocity. So 1/2 mv squared, right? Where m is the mass and then v is the velocity or the speed, right? So we also said that if you have one particle moving, you can calculate its kinetic energy. Well, if they're all moving, they all have kinetic energies, right? So there's a related equation that takes the average into account. It looks something like this. The average, so I'm going to put a line here for average. The average velocity is equal to the square root of 3RT over molar mass. Okay, so that equation, I'm not going to derive it for you. It essentially comes from this equation, because see how its velocity is the square root. Velocity is squared here. So if you want to find, velocity, you take the square root of both sides. So you have mass in here. This is molar mass over here. You've got the temperature in there. You've got the average kinetic energy. So the average velocity is the square root of 3RT over molar mass. So again, the point is that the hotter a gas is, the faster they move. They just start moving faster and faster and faster the hotter they get. But there's also this issue of how fast they're moving. How fast do they move? Well, the speed depends on two things. It depends on the temperature, right? So the larger this value is here, the larger this value is going to be here, right? The velocity will go up with temperature. But that makes sense. If they have more kinetic energy, they move faster. But there's also this, the molar mass, and that's in the denominator. So the larger this one gets, the molar mass, the smaller the velocity gets, okay? Those are the two factors. So when you look at these problems, if they're asking you, hey, I changed the number of moles, does that change the average speed or the average kinetic energy? No, the moles aren't important. What's really important is the temperature and the molar mass. So pressure, not important. Moles, not important. Just look at temperature. The higher the temperature, the faster they go. The higher the molar mass, the slower they go. Now, those are the two relationships, okay? So that one, and then you'll be set, okay? And that's essentially, there's all kinds of things we could do. We could even derive the ideal gas law out of this. We could derive Dalton's law of partial pressures out of this, Boyle's law and Charles's law. We're not going to go through all of that. That's something you would do maybe in a physical chemistry course, but it's all doable from this consideration, okay? So let me show you then. Let's see, let me close this here. Let me show you a problem involving graphs. Okay, so let me bring this up over here. Okay, so let me create a new one. All right, so let's consider graphs. So let's interpret a graph of molecular speed distribution. Okay. So it's very common when we're talking about gases to represent the speeds of these gases using a graph. So let me show you how you would do that. Okay. Typically, we have speed on the x-axis. And the speed could be in different units, but typically it's meters per second. Okay. And then on the y-axis, on the vertical axis, we have probability. Okay. And then the distribution might look something like this. Typically, it comes up, it's skewed to the left. So it looks something like this. Okay. So this is called a tail, right? If you've taken statistics, you've looked at, statistical distributions that have tails, right? This one has a tail. So it's skewed. And the x-axis starts at 0. So 0, that means they're not moving at all. And notice at 0, the probability that a gas molecule is moving at 0 is almost 0, right? It's down here on the y-axis at 0. It's at the origin of this graph. So that means, there aren't any gas molecules that are not moving, or if there are, it's very few. And then as we go along, we'll find that there's different speeds here. And these speeds are pretty large to what we're used to dealing with in our world, right? These are hundreds of meters per second. And just to put that into perspective, 1 meter per second is approximately 2.2 miles per hour. So if I say that a gas molecule is moving at 100 meters per second, you would multiply that by 2.2 to get miles per hour. So that would be 220 miles an hour. If I said a gas molecule is moving 200 meters per second, you would multiply that by 2 and you get 440 miles per hour. So they're moving pretty fast, right? So look at the way the distribution moves. This is 0 probability here. And then I'm not going to give you values up here, but you can see that as you go up the y-axis, the probability is larger. So the likelihood, the chances that a molecule is moving increases. Okay, so this is really where we see our maximum, right? Right there is our maximum probability. So that is where, the greatest, if you took one molecule at random out of the container, that's where it would most likely, that's its most probable speed would be right there. So if you take a look at where that is on this graph, it's around 200 meters per second. Okay. So that right there is about 200 meters per second. So the most probable speed, because that's at the highest value on the y-axis, is around 200 meters per second for that graph. Now, the way that graph looks depends on temperature. It depends on the molar mass of the molecules, right? Those are the two variables that we looked at earlier, temperature and molar mass. But these distributions look something like this, okay? So let's take a look at a question. So suppose we say that these are for xenon atoms, right? Xenon is a gas. It's a noble gas. It's a pretty heavy noble gas, but it is a gas. And the question was, what's the most likely speed of a xenon atom? What's the most likely speed? Well, that's what we already did that, right? It looks like it's right here, right? Because there's the peak. That's your maximum probability. You just move down to the x-axis. It looks like it's right around 200. So that's 200 meters per second. Okay. Now, there's another question we could ask, which is, what higher speed is only half as likely as the most likely speed? Okay, so what higher speed? What that means is higher than the average, higher than this peak. Sorry, higher than this peak. So we're going to be only looking over here in this direction, right? And we just want to go half. So here's what I'm going to do. I'm going to count up how many boxes we have on the y-axis. 1, 2, 3, 4, 5, 6, 7. It looks like it's around 7.5, right? The peak is around 7.5 boxes high. So I'm just going to go half of that. Half of 7.5 is around 4, right? That's around 4. So I'm just going to go up to 4. 1, 2, 3, 4. And then I'm going to read across. Now, remember, we're only looking at velocities that are higher than this peak. So that means we're only looking to the right of this peak. So right down there, and then we come down here, and it looks like that's, it's less than 350, right? So maybe it's around 340. So that looks like it's about 340 meters per second. Okay, so what that means is if you were to pick a xenon atom out of that container, the chances that it's moving 340 meters per second is around half as the chances are if you picked one out that it would be moving at 200 meters per second. So more are moving at 200, fewer are moving at 340, okay? Now we could ask another question, which is what higher speed? So that's higher than the peak is only 10% as likely as the most likely speed. Okay, only 10%. Okay, well, like I said, it was 7.5 boxes high. So what's 10% of 7.5? Well, it's 0.75, right? 10% is 0.75. So really it's going to be less than a box. So it's going to be all the way down here. So we're going to come all the way over here. And it comes down to about right there. So that's right there. That's around 560. Okay, so the point of this problem is just to kind of show you the nature of distributions. This is the sort of distribution that you see with collections of gas molecules. It's sometimes referred to as a Boltzmann distribution. And in a sense, it's really what it is it's a skewed normal distribution for those of you who have taken statistics. There's normal distributions and then there's skewed normal distributions, right? This is one that's skewed here. Okay. All right, let's see, what else do we have here for gases? The last issue is really like, can we actually do a calculation? Okay, this one's pretty easy, except the units. You just have to be careful with the units. So in this one, you want to do calculating the average molecular speed. Okay, calculating the average molecular speed. So in this type of question, what they do is they give you the average, or they ask you to calculate the average speed. In a sample of argon gas at 0.11 ATM and minus 58 degrees C. And so for this one, just be careful. They're going to give you the pressure and we don't really need the pressure. So just be careful. You don't need to have that in there. I gave you the equation a little bit earlier. We said that the average speed, oops, sorry, I used a V. The average speed was the square root of 3RT over molar mass. So there's no P in there. Don't worry about the pressure. Don't worry about volume, that sort of stuff. Just do the 3RT over molar mass. Now, there is a couple of factors here you have to be very careful about. One is make sure for R, you're using the 8.314 joules per mole Kelvin. Okay. 2, make sure the temperature is in Kelvin, not in degrees C, right? So Kelvin equals Celsius plus 273.15. Third factor, this one's not as obvious. The molar mass needs to have units of kilograms per mole, not grams per mole. Okay, that's an important thing as well. That's a common mistake. It's probably the most common mistake when you see people do these problems. Okay. The reason that that's there is because we're trying to figure out the velocity. So let me do a quick dimensional analysis here just to show you what's going on. Remember that if you're doing mathematical things or if you're performing mathematical operations on units, there are certain things you can do algebraically that are just like dealing with numbers or variables. So the joule is a kilogram meters squared per second squared, right? That's what a joule is right there. So for the units of R, it's joules per mole Kelvin. So there's a joule right there. And then we have mole Kelvin. Okay, so there's your R units. But then we also have T units, right? 3 doesn't have a unit, so don't worry about the 3. Units of temperature are going to be in Kelvin. So I'm just going to put Kelvin here too, up in the numerator. So there's your RT. But then in the denominator, we have molar mass. So we have a compound fraction here, right? So what are the units of molar mass? Well, as I said, you want to have them in kilograms per mole. And you can sort of see why that's the case here. Kilograms cancels with kilograms. So if you don't have the molar mass in kilograms, then that's not going to work there. Moles are in the denominator, Kelvin and Kelvin. So you're left with meters squared per second squared. But again, you're taking the square root of that. So you take the square root of the units also. So you get meters per second. So be careful. This last one right here, if you don't convert it to kilograms per mole, you're going to be off by a square root of 1,000. Okay, so you'll be off by like 30. So your answer will be incorrect. The other thing, make sure that you're in Kelvin and make sure you've got the 8.314 joules per mole Kelvin. And again, that's based on the fact that a joule is a kilogram meter squared per second squared. Isn't that cool? All right. So let's go through it now. We're talking about argon gas. So argon is 39.95 grams per mole. Is that right? I think it's 39.95. It's cool. So let's convert it to kilograms per mole. 1 kilogram is 1,000 grams. So there's our grams canceled. So you get 0.03995 kilograms per mole. Easy conversion, just divide it by 1,000, and that'll get you from grams to kilograms. Okay, the moles are not changed. You have moles in there. Temperature, we had, what was it, minus 58 degrees Celsius. So your Kelvin temperature is your Celsius, so minus 58, add 273.15. Okay, so what is that? 73 minus 58 is 25. So it looks like it's 225.15 Kelvin. I'm going to leave the 0.15 in there. Okay. So we got our molar mass, we got our temperature, R we already have. We can calculate the average speed. Square root 3RT over molar mass. We already did the dimensional analysis, so let's just put the numbers in. 3, remember our 3 doesn't have units. 8.314, there's your R. 225.15, there's your T. And then you're going to divide that by 0.03995. And that's going to give you the units that we already figured out, meters per second. Okay, don't forget to take the square root. So 3 times 8.314 times 225.15 divided by 0.03995. And then you take the square root and you get 375. Now keep in mind that right there, that's not all that different from the graph we just looked at. Remember we looked at the graph? Okay, I didn't skew that very much, but remember we had probability and then we had speed here. So really what you're calculating here, it's a little bit to the right of the peak. It's not the peak you're calculating a little bit to the right. And the reason it's a little bit to the right is that the graph is skewed, right? So it's skewed, so you're going to be a little bit past that right there. So there's your 375. Okay. And that's what that you're just calculating that one speed on that whole graph. If you want to calculate everything on that graph, what you'd have to do is you'd have to run it through some more complicated formulas that we're not dealing with in this course. Okay, so there you go. So remember 8.314 temperature in Kelvin, divide by 1,000 to get the units of molar mass in kilograms per mole. Take the ratio, take the square root. You'll see a term in there called root mean square. That's just the way that the average is computed. There's different ways of computing averages. And the root mean square is where you take a number, you square it, you add it to the next number that you square, you add to the next number that you square, you add them all up, and then you take the square root of it. That's called the root mean square, but we don't need to worry about that. That's just a detail of how the average is computed. I'm just going to use this little notation right here, but you could also write it this way, VRMS. You might see it like that too. Okay, so for our purposes, VRMS is the same as V bar. Okay, and then that's pretty much, that's it for the gases. You don't have to do much more than that. There are some other types of problems that people sometimes do, but we don't need to worry about those. Okay, and that's pretty much it for gases. So we went through a lot though, think about it, right? We did pressure conversions, atmospheres, kilopascals, all of that. We did Boyle's law, P1 V1 equals P2 V2. We did Charles's law, V1 over T1 equals V2 over T2. We did Avogadro's law, V1 over N1 equals V2 over N2. We also did Dalton's law of partial pressures. The sum of the pressures is equal to the total pressure with mole fractions. We used the ideal gas law, but we also used the ideal gas law for chemical reactions and stoichiometry. And then we got into the kinetic molecular theory of gases and did these calculations here. So quite a bit in that chapter. It's a lot in there, but most people usually do pretty well in this chapter. So just keep at it, you'll be fine. Okay. The next thing I want to start working on is really what we might call the second half of the course, but it's not going to take half the time. It's really about the last third as we go through it. And that is quantum chemistry. So we're going to start with chapter 6. And this is really quantum chemistry. Okay, so I'm not going to go through the whole title here. It's a pretty complicated title. It's called like Quantum Theory and the Electronic Structure of the Atom, but that's where we're headed, is into that. Okay, so we're going to begin by considering, I'm trying to figure out, we could go through so many things. There's such a rich topic, but let me just give you a little bit of a background. And then once we go through the background, we can take a look at some of these problems. So the issue is that although we have these equations that can predict the behaviors of gas molecules very well, the electronic properties of atoms, those sorts of equations don't work very well for them. So there are some certain issues that people are dealing with to deal with the atom. So let's come back to our picture of the atom, right? This is kind of a cartoonish picture. Sometimes you'll see this where they have a bunch of little particles in the center, which is representing the nucleus. So that's your nucleus. And then they'll show, I mean, it's kind of a cool picture. It's just that it's inaccurate. They'll show these like little orbits around them, right? There we go. And those little orbits are representing the motions of electrons. So the picture here is that the atom is this little central region with these little particles, which we call protons and neutrons, right? So this is the nucleus. It's got the protons, which we can represent as P+, and it's got the neutrons, which is N, right? So that's the nucleus, and then these electrons are in orbit. Now, sometimes it's actually useful to use a picture that's a little bit like that, but it's often the case that it just doesn't work very well. So what we're going to do is we're going to take this This is often referred to as the nuclear model. And we're going to modify it into what's called a quantum mechanical model. And this one's more modern. This is the modern theory of the atom, okay, which replaces this nuclear model, okay? As nice as the nuclear model is, that's what we're going to do, okay? So again, we're going from the idea of this like little center here with the protons and neutrons, and then these electrons whipping around. They're just whipping around real fast around the nucleus, okay? So here's how we're going to deal with this. What we're going to do is we're going to say, suppose we have some atoms and we want to study them. We want to figure out what they're made of. And we already know that, right? Electrons, protons, and neutrons. But we want to know like what's the kind of internal structure. So think of it this way. Suppose I had a box and there was something in that box, but you didn't know what it was. So there's something in there, but you don't even know what shape it is. You don't know what it's made out of. And you can't look in the box and you can't stick your hand in the box. What would you do? You'd probably shake it, right? You'd shake the box to try to get an idea. Is it hard? Is it soft? Is it bounces off the walls? Is it big? Because if it's really big, you're not gonna feel it moving around very much. But if it's small, you'll feel it moving around a lot. So, there's certain things you can do. Now with atoms, there's something we can do with them. There's a couple things. One is we can heat them. And it turns out if you take atoms and you heat them up to a high enough temperature, they glow. Which means they release light, right? They're emitting light if they get hot enough. So you can see this all the time, right? An example would be a flame. If you're burning something like a match, what's happening? The atoms are getting heated up to such a high temperature, they're emitting light, and light is actually, escaping. Light actually has energy. We'll talk about that. So it's actually losing or emitting energy through light. The sun does that, right? The sun is sending light. So heat a gas, in fact, that's what the sun is, right? It's a hot gas. So they glow. But it doesn't have to be a gas. It could even be a solid, right? That's essentially the basis of these like old electric heaters that you would have on a stove, right? If you turn them really hot, it glows red, right? It glows red, and that means that it's really hot. It turns out the temperature of a star determines its color. So our star, the light's pretty white, actually. It's sometimes referred to as a yellow star, but the light's pretty white. It's pretty much all the visible colors. Some stars are blue, and some of them are red. And so if something is red, that generally means that it's a little cooler than a white star. And if something is blue, that means it's hotter than a white star. So the color is actually affected by the temperature. Okay, so stars are different colors. Some people have really good vision, and I think they can actually see the different colors of stars if they look at them. But telescopes can definitely see that. So, it doesn't have to be a gas. It can also be a solid. So they release. But another thing they do is actually absorb light. And a good example of this is this thing called ozone. You've maybe heard of it. Ozone is trimolecular oxygen. You might call it trioxygen. Okay, it's O3. And it's kind of an interesting molecule. It has a bent shape like this. It's 3 atoms bent like that. And what's significant about ozone is that it's produced in our atmosphere by taking molecular oxygen and atomic oxygen, so O2 plus O, and they'll react to form O3. But here's what happens. Ozone can actually take ultraviolet rays that come from the sun. So solar ultraviolet radiation, we call it. And what happens is it absorbs that radiation and breaks up into O2 plus O. So it's absorbing the energy of that ultraviolet light. And the importance of that is that that ultraviolet radiation is very dangerous energy. It's very high energy. So it will essentially destroy cells. It will kill cells. So at the surface of the earth and even in the oceans, that type of radiation, if it were able to reach the surface, it would kill plants. So you wouldn't be able to grow food. It would give cancer to animals. It would give cancer to humans. And it's even estimated that ozone depletion in certain parts of the world have raised cancer rates among humans. But it would actually kill crops. It would kill all, all sorts of plants. So for that reason, it's important, this ozone molecule. So they can absorb, my point of this is that atoms can absorb radiation as well. So atoms can absorb light. So two things. If you heat atoms, they glow, which means they're releasing light. And if you send light in, they can absorb the light. So that is something that's different than this box. In this box that we're rattling around, we don't have a way to send light through there, through the box, to study it. But in the real world, we do, right? Atoms can be studied by heating them, seeing what light comes off of them, and then shining light on them to see what kinds of light that they absorb. And it turns out that different atoms absorb different colors of light. That's one important aspect. So you can actually identify what atom you have in a sample just by looking at measuring the colors of light that come off of it. You can do it very crudely just by dipping it into a flame and seeing what color you see. So different sodium, for example, emits like a yellowish orange color. But also the other thing is that different atoms, when heated, emit different colors of light. That's pretty cool too. Let me do this. Let me see if I can bring this up here. Oh, right. Okay, so let me bring this up. Okay, let me share my screen here so you can see this. Here we go. All right, so I think you can see this now. If you look at this, these are different stars, okay? And so here at the top here is 5,000 Kelvin. This is called a G-type or a sun-like star. So that's a star like ours. And take a look at this distribution of colors. So these are all different colors. We'll talk about wavelength in a little bit. But these are the different colors of light. See here in the middle is the rainbow. So you've got violet all the way through red. Those are the visible light that we can see with our eyes. To the left over here is called UV or ultraviolet light. We can't see that with our eyes. Some people can see a little bit of ultraviolet if they have really good vision. Most people can't see very much ultraviolet, but there are animals that can see ultraviolet. Okay. And then over to the right of visible light is what we call infrared radiation or infrared light. So to the right there are different colors that we just can't see. Again, some animals can see infrared, and we can build machines that can see those colors, right? So we can build infrared goggles. Those are often referred to as night vision goggles. Those are just seeing in the infrared and converting it to visible light so that we can see it. There's also sensors that can measure ultraviolet. So if you take a look then, you know, each different star, depending on what temperature it's at, is going to have a different color. So this one right here, this is called an M-type red star. It's colder, so it has a different color. It's red. This one over here is 4,000. This is a K-type orange star. So that one's at 4,000 Kelvin on average. So it's going to have that particular color as well. So keep in mind, what you're seeing are distributions of colors. There's a lot of colors in there. It's just that for us, when we see lots of different colors, we perceive that as a dominant color, as a primary color. Okay. So let me show you the electromagnetic spectrum. Find an image here. There we go. This one, let's try this one here. Okay, that one's showing up. There we go. That's a little bit better, right? A little bit bigger. Okay, so here's the electromagnetic spectrum. So what this does is it shows you all the different colors that exist in the universe, in our universe. Okay, all the colors of what we call light. But for us, we often think of light as just being this little sliver right here, which appears to be pretty close to the middle, right? That little stretch there is what we call visible light. That's all the colors that you're aware of. This is violet over here. This is indigo over here. This is blue over here. This is green over here. This is yellow. This is orange. And then this is red. Okay, so what they've done is they've taken this little sliver and they've broken it out to make it bigger just so that you can see it bigger. So everything that we think of as colors, unless you have some sort of special vision, is Roy G. Biv. Red, orange, yellow, that's Roy. G, green. Blue, indigo, violet, Biv. So you'll sometimes see that, Roy G. Biv, B-I-V, for the colors of light. So if you heat atoms up or molecules, they will emit light at some color. So a light bulb, what does it do? A light bulb emits colors in the visible range, in this stretch through here. So you design the light bulb to emit the colors that are useful for us to see. There are some light bulbs that only emit red light or primarily emit red light, and they appear red. Okay. Sometimes those are used for camping. Sometimes they're used in in photography laboratories where you don't want much light to expose the film. But notice there's also ultraviolet. The sun emits ultraviolet. Some stars emit X-rays. Actually, black holes emit X-rays. Some incredibly energetic processes like supernova emit gamma rays. Certain atoms are unstable and they slowly emit gamma rays over years, over thousands of years even, okay? So there's different types of light or different types of what we call electromagnetic rays. There's infrared, right? So infrared is where, you know, that's the night vision goggle. We ourselves are actually glowing light because we have a temperature, right? So like we're warm-blooded, we're emitting infrared radiation at all times, okay? Now, there's something that's not shown in here, and that's called microwaves. Microwaves is over here. They call it radar because they're talking about technology here, but it's called microwaves is radar. And microwaves are used for cell phone communications, for Wi-Fi, things like that. And then we get over here to FM. That's radio, right? FM radio. So that's like, you know, Z100 or, you know, all those FM radio stations that people under 40 don't listen to. Then you've got TV, and then you've got shortwave radio, and then you've got AM radio, right? So those, you know, that's the 1010 winds kind of stuff over there on the right. So this is called the electromagnetic spectrum. the EM spectrum. And these are all the different types of electromagnetic waves or rays that are emitted through different processes, right? So electronic circuits can emit or absorb AM, shortwave, TV. That's why we plug them into the wall, right? Radar, all of those things are radio waves, essentially. Then you get your infrared. This is due to things kind of glowing because they're hot, including us. And then you get visible light. Things have to be really hot, right? Like, so you're not going to get a piece of metal to glow unless it's really hot. But if they get hot enough, they can emit ultraviolet rays, which our sun does. Our sun's very hot. They can even emit X-rays. So some stars emit X-rays, but they're even hotter. And then radioactive processes and all of that, extreme processes, can emit gamma rays, okay? A supernova, for example, can emit gamma rays. So visible light, Roy G. Biv, electromagnetic spectrum, the whole thing. Notice that they've got something here called wavelength, okay? And there's scientific notation there. So that's one of the things we're going to talk about. Again, the reason we're interested in these electromagnetic spectrum is because it gives us a way to study the atoms. It gives us a way to study the structure of the atom. Once we get into talking about electrons, it'll all kind of come together and it'll make sense, okay? So the first thing that generally we want to do is to take a look at doing some calculations involving wavelength and frequency and then energy as well, okay? So let's take a look at doing some interconversions. Okay, there we go. So let's do some interconversions. Of wavelength and frequency. So when we talk about electromagnetic radiation, so I'm going to write this down, electromagnetic radiation. Okay, so that could be coming from a light bulb, right? You're emitting electromagnetic radiation. Could be coming from a hot star, right? The sun, right? So here's your sun. It's emitting electromagnetic radiation. It could be from a person. People are emitting electromagnetic radiation in the form of infrared. We're certainly not as hot as a light bulb and definitely not as hot as the sun. So the types of electromagnetic radiation that we emit are different colors, right? They're infrared as opposed to visible or X-rays or ultraviolet, okay? So there are two ways, actually I should say there's three, but we'll start with two ways. Two ways of quantifying these EM meaning electromagnetic radiation. We'll look at a third tomorrow. These two are what we call wavelength and frequency. Okay, now there are different symbols that are used, but typically wavelength is lambda, lowercase lambda, lowercase l, I guess, if you want to think of it that way. This is called lambda. It's a Greek letter. Frequency is typically an F, but your textbook may use this, which is called nu. Also a Greek letter. So you'll either see F for frequency. Physics books typically use F. Chemistry books sometimes use a nu. Okay, those are two ways to quantify, to measure electromagnetic radiation. And they're both based on the idea that radiation, EM radiation, I should say, because there's other types of radiation, are comprised of waves. Okay, that they're essentially waves. So think of a wave like an ocean wave. We'll talk about a little bit more about waves as we get through this, but I just want to give you the basics of this so you can do the calculation. So think of a wave as an oscillation, something that's a repeating pattern that goes up and down, right? So like the ocean, sound waves are actually vibrations of air that are going up and down. Okay, there's all kinds of different types of waves. You could think of a string. If you're vibrating a string, that's a sort of wave as well. Okay, so the wavelength is just the distance between the peaks. So this is called the wavelength, all right? The frequency, oh, let me use F. I'm not going to use V and U. Let me use F. So let's write it this way. Wavelength is the distance between the peaks of the wave. So it's typically in meters or micrometers. Those are the units. Centimeters, nanometers. So they're in length units, right? Because it's the distance, right? You're measuring distances. Okay. And then you got frequency. Now let's talk about frequency. So frequency is a little different. Frequency, we have to think of in terms of time. So the easiest way I would say is imagine that this wave that I'm representing here is the height of something that's changing over time. Okay, so it's going up and down and up and down. So think of an ocean wave, right? If you look, the wave goes up and then it comes back down. It goes up and then it comes back down. It's changing over time though, right? The waves are changing over time. So how fast is the wave changing? So the frequency is how fast does the wave change? Okay. And it's typically done in cycles per second. So how many complete cycles of the wave do you have every second? You could have 10 cycles per second, 10 complete vibrations of the wave, or 20 per second. And so the units, a cycle is not a unit, but a second is. So the units are 1/seconds, S for seconds, or sometimes it's written this way, S to the -1. Now, that's awkward, right? 1/s or S to the -1, that's just awkward. So we give it a name. The units are typically called hertz. And the abbreviation is HZ. So if you see HZ, that means hertz. And then that means cycles per second. So 25 hertz would be 25 cycles per second, complete cycle, okay? So you have these two ways of measuring the waves. One is essentially how big the wave is, how long it is. That's called wavelength. How long is it? The other one is the frequency, which is how rapidly is this wave changing? And typically that's done as cycles per second or hertz. Now, the reason those two are useful for us is they're related to each other. The wavelength of a wave, this goes for any wave, times the frequency of a wave is equal to its speed. And this turns out to be very useful because what it allows us to do is it allows us to measure how fast a wave is moving, measure the wavelength, and then find the frequency from that. Or measure the frequency, measure the speed, and then get the wavelength from that. And we can interconvert them. Okay, so let me use the symbols for this. Wavelength is lambda. I'll use a dot instead of time, instead of an X. Wavelength times frequency equals speed. Now speed, we've used V for velocity, U for velocity, but when we're talking about waves, we use a very specific symbol, and that's a C. So this is the speed. This is a symbol of speed that we use with waves. Okay. You've seen that symbol in your past. You've seen it in terms of Einstein's theory of relativity, E equals mc squared. The C that's in that equation, right? You've seen this? That's the speed of electromagnetic waves in a vacuum. That's where that comes from, okay? So we're talking about the speed of a wave. Electromagnetic waves are the same as electromagnetic radiation, okay? Or for our purposes anyway. So here's our equation, and this one is kind of nice. So let me show you an example. Just it's a very simple problem. These are really easy. The only thing that can trip you up typically are the units because they're going to give you prefixes, okay? So let me show you an example. I'm going to stop share on this one. I'm going to share this screen just so you can see this problem because there's a lot of words in here and I want you to see it. Okay, so share this one right here. Okay. Okay, you can maybe read this a little bit better now. So it says here, infrared radiation from young stars can pass through the heavy dust clouds surrounding them, right? So imagine you have these young stars, like our star was 4.5 billion years ago. It just ignited, it's now producing radiation, this shining light, but it came from a dust cloud. That's where these stars come from. They're formed in dust clouds. So these young stars are typically in a big dust cloud. We sometimes call them nebula. Surrounding them, allowing astronomers here on the Earth to study the early stages of star formation before a star begins to emit visible light. Suppose an infrared telescope is tuned to detect infrared radiation with a frequency of 1.54 terahertz. THZ is terahertz. Convert the wavelength of the infrared radiation, okay? So, you know, despite the paragraph of describing what's happening, it's actually a pretty simple problem. So let me stop share this one and share this one. Okay, so here's our relationship, lambda times frequency. Ooh, I made that same mistake. Times frequency equals speed. And here what we're told is that the frequency of these infrared waves is 1.54 terahertz. And we want to find the wavelength. Okay. Pretty simple problem, actually. So let's go through it. We have 1.54. So I'm going to show you the prefixes here. When you're talking about frequencies, they're usually very large. So here's our prefixes. You have kilo, right? Kilo is K, 10 to the 3. That's 1,000. You've got mega, capital M, 10 to the 6. This is the prefix that's used for AM radio. So when someone says, oh, I was listening to the news on 1010, what they meant was 1010 kilohertz, 1010 kilohertz. That's the carrier frequency. Megahertz is typically used for FM radio. So AM radio, FM radio. Okay. Then we have giga, right? So giga is typically used for microwaves. Okay. So giga is G, 10 to the 9. Oops, 10 to the 9. There's your, Wi-Fi, actually. Wi-Fi and cell service. That's where that's used. Then you get tera. Tera is a capital T, and that's 10 to the 12. And this is when you get into infrared. Okay, so infrared is tera. Okay, so there's one more piece of information we need, and that is what is C equal to? C, the speed of these waves, is 2.9979 times 10 to the 8th meters per second. It's a very large number. That's a very high speed, right? 10 to the 8th meters per second. That's fast enough that you could get to the moon and back in about 2.5 seconds. Is that right? Yeah, about 2.5 seconds round trip to the moon. Okay. If you put a satellite just a couple hundred miles in orbit, you could bounce light off of it. You could send radio signals from it, and it would be much less than a second. Okay, so there's our speed. Doesn't matter what type of electromagnetic wave we're dealing with, we're going to use that value. Technically, this is in a vacuum. We're not always in a vacuum, but we'll use it for our calculations. So here's our question. What is the wavelength? So you start with this. The wavelength would be the speed divided by the frequency. You just divide both sides by frequency. And then you put your numbers in. 2.9979 times 10 to the 8th meters per second. Speed. Now, what about tera? Tera is 10 to the 12. So 1.54 times 10 to the 12. That's 1.54 tera. What's a hertz? 1 over second, right? So hertz is 1 over second. So I put 1 over seconds. Look what happens to the units. The seconds are in the denominator both times. So you just get meters over 1, which is just meters. And wavelengths can be in meters, they can be in nanometers. In this particular problem, they don't tell you which one to put it in, so you can just leave it in meters. So 2.9979 times 10 to the 8th over 1.54 times 10 to the 12th. And you get a small number. You get 1, I'm going to round it to 3 sig figs, times 10 to the minus 4. And there you go. So that's your wavelength of this IR radiation. Okay, 10 to the minus 4. Now that's pretty small, right? What that means is if you were to measure these waves, these infrared waves, the distance between the peak, 2 adjacent peaks right next to each other, is, 10 to the minus 4 meters, 1.95 times 10 to the minus 4. That's pretty small, right? A meter is about a yard, right? It's 39 inches, about like that, 100 centimeters. A tenth of a meter, 0.1 meter, is about that big. That's a decimeter. Almost no one uses decimeters. And then a centimeter is a hundredth of a meter, so a tenth of a decimeter. So a centimeter is about that big. And then a millimeter is a tenth of a centimeter, so a millimeter is about that big. A tenth of a millimeter, you can't even really see that very well. You're right on the edge of what you can see. So that's actually pretty small. That distance is so small, you can't really see that with your eye. That's 2 times 10 to the minus 4. That's about 0.2. But actually, some people have really good eyesight. So it's about 0.2 millimeters. So you could maybe see 0.2 millimeters. Okay, that's getting close to the limit of what you can see. All right. Okay, so what we're going to do when we come back tomorrow is we're going to look at quantum theory. So we're going to start doing more of these kind of interconversions. And we will look at Bohr's model, and then we'll start getting into the quantum mechanics. Right now, all we've done is looked at electromagnetic waves. We haven't connected this to the atom. The real reason for this is we want to know what the structure of the atom is. So what I'm going to claim is that we can use these waves to study the structure of the atom, to figure out what its internal structure is by sending these waves in or measuring the waves that come out. That's essentially how we see things, right? Light bounces off of something into our eyes and then we perceive it and process it. Essentially, we're studying things by using these waves. Okay, so have a great day. Reach out to me if you have any questions. And again, the lab reports, the third one, I'm going to start working on them this afternoon. Should be done by the weekend. And take care, everybody.
Thank you, Professor.
Bye-bye.